Okay, today we are going to learn how to do another method of finding the volume. Let's say we have this region, y equals x, and part of the circle, y equals the square root of 4 minus x squared, and create the region between that, the y-axis, and we're going to rotate that region around the y-axis. And in order to do that, we're going to go ahead and reflect the region. So I will first reflect the line across the y-axis, and then I will also reflect the part of the circle around that y-axis. It's important for us to figure out what that point of intersection is. We're going to need to know it one way or the other, but this is revolved, so I'll draw the revolution. Looks kind of like a snow cone. One of the things we could do is we could find the volume of this shape using our discs. This is a completely solid shape, so we could use discs to do that. The one issue we would run into is that we would have to use two different integrals because the radius of the disc would depend on two different functions as we began to stack them. So what I would do is I would lay this first disc down in the bottom region of this snow cone, and the radius of that disc would depend on the line. But then in the top region, as I continued to stack these discs on top of each other, in the top region, the function that the radius depends on would change, and so I would have to stop and create a different integral. So what we're going to do is we're going to change the way we think about stacking things, and rather than stacking discs on top of each other, we're going to take a hollow shell or a hollow can and start to stack these things around each other. And so we need to stop and think about these hollow cans, because remember, our integral sign is just our ability, so to speak, to add up an infinite amount of something. And what we're going to try to do is we're going to try to take these hollow cans and start really close to the y-axis and continue to stack them around each other and fill this area up, sort of as we moved across the x-axis with our from one shell to the next. So if I try to draw one of these shells in here, an arbitrary shell might look something like this. And again, remember, it's rotated. That's the best I got for that three-dimensional shape. But we need to know something about what kind of formula should we write when we add an infinite amount of something together? Because what we're going to do is we're going to create this definite integral. Now, in order to figure out what we're going to add together, we have to think a little bit about each one of these individual shells. What I know about these shells, or these hollow cans, is that each shell is going to have a radius, each shell is going to have a height, and each shell, because it's hollow in the middle, is going to have a thickness, kind of like the thickness of the wall of the shell. And we need to find the volume of that wall of the shell, and the way that we do that is kind of if we took a piece of paper and rolled it up and then unrolled it, we would do length times width times height, kind of an idea. And the length would be 2 pi r, the height is h, and the width would be the thickness of each one of these walls. So now if we go back and we start to apply that to the shells that we have kind of drawn in our shape or in our object here. Whoops. Let's try that again. What I have at the top is I have a radius, and that radius is going to go from the axis of rotation, and it's going to move on out from the axis of rotation, which is the y-axis, out towards wherever I end up stopping. And the radius is just going to be an x value. It's not going to depend on a function. It's just going to depend on the range of values that we use in our definite integral. So the radius is just x. Now I also have to start to think about the height of each one of these shells as I stack them around each other over and over and over again. And the height of each one of these shells is going to be the difference between these two functions here. And just like area between curves, just like everything we've kind of always done, when the height is between things, it's just a quick subtraction problem or a difference problem. And so we're going to do top minus bottom here. And so really what this is this is the difference of the y value of that top function, which is the square root of 4 minus x squared, and the y value of that bottom function, which is y equals x. And then our thickness is that very small change in x dx. I'm going to stack these from x equals 0 to x equals the square root of 2. That comes from the point of intersection.